Good afternoon, thanks you for coming. Sorry about the delay there, technical hiccup. Turns out this embedded Linux ARM stuff doesn't talk to HDMI very well. And I'm just going to unplug the network to stop that happening. This talk is an overview of the current status of the SPI subsystem. I'll introduce you to what SPI is. I'll talk about how SPI works in Linux, and then go over some of the work that's been going on recently and go on to cover some future plans for the subsystem. If at any time you have any questions or comments or clarifications you'd like, feel free to just interrupt as we go rather than waiting for the end. So, what is SPI? SPI is a simple bidirectional serial bus. It's not standardized at all. It's just defined by convention, but because it is so simple, and because device manufacturers have a desire for their devices to be interoperable, it's reasonably consistent. And the differences between the variations on the SPI protocol are really very small and not at all apparent to the software stack. It's just an option you set once the system startup and leave and ignore. So the classic SPI bus consists of 4 data signals. There's a data out from the CPU to the peripheral, master out, slave in, normally referred to as MOSI. There's data coming back in the other direction, master in, slave out, referred to as MISO. There's a clock to which all these, both these signals are synchronized. And there's another signal called chip select, which is a simple logic level, which tells the slave device that it should pay attention to what's going on the bus. This is used to implement an addressing scheme. So you can have more than one slave device connected to a master, and the slaves that aren't active at the minute will just ignore things if their chip select isn't asserted, assuming the hardware isn't buggy, which wouldn't be the first time. There's no protocol at all defined for the data on the bus. However, by convention, devices tend to implement little-endian words, so many SPI controllers have support for doing byte swapping to little-endian in hardware. In terms of software, it's very easy to think of it as compatible to I2C. It's got 4 wires instead of 2, and it's much simpler, both in terms of hardware and in terms of the software model. Because it's simpler, it can typically run about 1 to 2 orders of magnitude faster than I2C. So typically I2C would run up to about 400 kilohertz, whereas a SPI device would normally be controlled at something between 1 to 30 megahertz, although given the lack of standardization, any speed is possible. SPI is also faster because it's full duplex, so if you've got an application that needs to send and receive data to a device, it can do both at the same time. It doesn't have to wait for the bus to become idle before it can switch from one to the other, and there's no overhead for addressing really. It's just asserting a logic level. So typically SPI gets used in applications where either logic is very expensive or you need something that's physically simple but fairly high performance. So the most common thing you're likely to see is SPI flash. Many SOCs will boot from an external flash connected via SPI. SPI is nice and simple to implement in both the hardware and the bootloader, but it works reasonably fast, so you're not sitting there for ages waiting for the CPU to read data out of its flash. It's also commonly used in mixed signal ICs. These are implemented using larger process nodes than typical digital ICs. This means that every bit of logic used for control is more expensive than it would be on a digital IC, so something that's simple is a big advantage. And often the data rates for things like ADCs and DACs are relatively high, so you need something that's fast as well. The other common thing you see is DSPs. Little small external DSPs are often controlled using SPI because it's simple, and sometimes they're integrated into mixed signal ICs. And again, they tend to need high data rates like the mixed signal ICs. but they want to be implementable in hardware with reasonable ease. You don't want to be dealing with a parallel data bus, which makes the hardware engineers sad and have to work hard. So, and because I've done, my slides aren't working as I expected, never mind. So what does this look like in terms of the controller hardware? What do we have to deal with as software engineers? Well, the very simplest SPI controller is no SPI controller at all. It's just to bit bang everything using GPIOs. This is obviously really, really slow and inefficient, but in some applications, that's okay. In some applications, you don't need to talk to the device very often, so you can get away with it. And because SPI is nice, simple, and easy to implement, you can get away with doing that. It's also very common to bit bang the chip select signal because it's very simple to do that. And it means that if the hardware designers have implemented a chip select that isn't ideal for what you need to do, then you can just ignore them, or you can use another signal for chip select if there's some sort of pin muxing conflict or something. Like I say, this isn't great for performance though. The next step up in performance, and the first real SPI controller you'll see, is a simple PIO-based FIFO. So you have a register that you write the data you want to send into. You have a clock signal. When you write a word of data in, you hit go. The peripheral will clock the data out, and it will clock any data coming back in, and then you can read the other data back from another register, typically with an interrupt when it's finished. Doing this per word is really expensive, especially in terms of interrupts. So most controllers that do this will actually implement a FIFO, so you can read and write multiple words of data in a single transfer. This saves you the majority of the work from bit banging, but it does require a CPU access for every word, which is quite a bit of overhead, especially if you've got a very fast CPU talking to peripheral on a slow external bus, so an AHB or something. So for large amounts of data, this isn't great, and instead you're better off using a DMA controller to fill the FIFOs and drain the FIFOs. This is obviously less work for the CPU when doing the individual data transfers. However, it does have a higher setup overhead, usually, so it's not necessarily going to be faster for small interactions with the device. But for large blocks of data, it will almost always be a win. So what you'll see in a lot of SPI drivers is they will use PIO for, say, 4, 10, 16 bytes, and they will then switch to DMA at some point. That's about as fast as you can make a SPI controller without extending the protocol, but it's not fast enough for some applications, especially for flashes. So people have started defining extensions to the SPI protocol which add extra data lines. There's dual mode, which repurposes the master out slave in line as another input line. And there's quad mode, which does the same thing, but adds another 2 data lines in parallel as well. Nobody's really gone beyond that, because once you've gone beyond that, you're up to 8 bits, and really you've just implemented a parallel bus and it's not SPI anymore. The final thing people have done, which isn't dealt with in the SPI subsystem at all, so I'm not going to talk about it at all in the rest of the talk, is that they've implemented specialized flash controllers which understand the protocol used to talk to flashes, which is standardized, and can implement operations with single register writes to trigger them and things like that. These are usually very, very hard to use as actual general purpose SPI controllers. They're usually only usable as flash, so they're implemented in the MTD subsystem with no involvement from SPI at all. I say I've mentioned them mostly just for completeness. And, wonderful. So in software terms, what does this look like? Well, as you'd expect, it's a standard device model bus. We have controller drivers, and we have device drivers. The controllers are instantiated using whatever bus they're connected to. The devices are manually registered by something, since SPI is non-enumerable. In the past, this was always done using board drivers. These days, it's done using DT, or we've recently added ACP support as well, for those of you using ACP. No hands. the big picture has been basically unchanged since SPI was originally contributed in 2006 by David Brownell. It's very, very standard, perfectly normal Linux bus. The interface offered to devices is fairly straightforward. Interactions with the device are modeled as a thing called a message. Each message contains a list, some parameters, and also contains a list of one or more transfers. These are actual interactions with the device. The message just models the assertion of chip select, and the transfers are the clocking of the data. The reason why we can have multiple transfers is so that we can implement scatter-gather. So we can take data from several places and put it on the bus, or take it off the bus and put it in several places. And also allows us to mix read-only and write-only sections of the message. So if you're doing a read from a device, you'll typically send some sort of command to the device and then read the data back in a follow-up transfer. You can vary settings for the bus. So for example, the speed or the number of bits per word, if the controller supports changing that, on either a per transfer or per message basis. There are a few things that can only be set per message, but most things can be set either per message or per word, or indeed when the device is registered. And optionally, the API is asynchronous. So in code terms, this is fairly straightforward. You have the transfer, which has a transmit buffer and receive buffer. There's a length specifying how long the transfer is. So you create your transfers, you initialize a SPI message, you add the message, add the transfer onto the end of the message, and then you call either SPI async, which is the asynchronous interface. It will request that the transfer is started, but then return immediately. You can set a callback in the SPI message to say when it's complete, or you can call SPI sync, which will provide a default callback and then wait until the transfer is complete. Almost all users use SPI sync. There are very few users of SPI async, most of which are in frameworks rather than in individual drivers. The reason you would use, or there's two reasons why you would use SPI async. One is that it will give you a bit of a performance boost if you use it well. And the other is that SPI async, because it doesn't block, can be called from interrupt context. So if you're handling an interrupt from a device, you can kick off the processing of that interrupt in the interrupt handler in hard IRQ context without having to schedule a task to do the interaction with the device. On the driver side, the interface is very, very basic. The only thing you really have to implement is a function called transfer. This is called whenever SPI async is called. It takes the SPI device to interact with. It takes a SPI message to send. And it's responsible for ensuring that the transfer is carried out, all the settings are applied, and that the completion callback is called. And you can't just do something simple like interact with the device with a big mutex held so that there's no contention, because this is called from SPI async, so it needs to be possible to execute it in atomic context. Clearly, that's a lot of work and not very, very satisfactory for driver authors. So all the initial SPI drivers that were merged when the framework was merged used a framework called SPI bitbang, which was included along with the main framework. This deals with most of the complexity of implementing transfer in this asynchronous context. It provides a framework which takes the message, queues it up in atomic context, wakes up a thread which will go and actually do the transfers, and calls into the driver to perform driver-specific operations that aren't generic. So you get three functions. You get setup transfer, which sets the hardware up in the correct configuration for the transfer. You get chip select, which asserts and deasserts chip select. While I said that the message models the assertion of chip select. There are actually some things you can do within a message to play around with chip select. So it's not completely trivial to handle chip select. And there's a TXRX buffers function, which is called to do the actual interactions with the device. So this factors out all the complicated logic, or most of the complicated logic, which is nasty for drivers to implement. And it can actually support drivers that want to do DMA. There's no reason why you can't do anything you like inside TXRX buffs. But the framework is called SPI bitbang. So what actually happened was that lots and lots of drivers that could use SPI bitbang didn't, and open-coded everything. And that's really been the biggest problem with the SPI subsystem for most of its lifetime. There's been very, very little code reuse outside of SPI bitbang, and lots of things that could use SPI bitbang didn't, because I suspect that the driver authors looked at the name of the SPI bitbang framework, then when I have this fancy DMA-based controller, it can do all sorts of things, it's not doing bitbanging at all, and didn't even open the source file. So what we've ended up with is lots of SPI drivers implementing roughly the same stuff with lots of wheels of varying shapes. Some of them are rounder than others. And a lot of these drivers, or several of these drivers, have actually implemented a bunch of really good ideas, but they've been implemented in the individual driver, and if another driver wants to pick them up, they need to be copied, which is unfortunate. So that's been the biggest focus of the work on the SPI framework recently. I should also say that there are some optimizations, which I'll come on to a bit later, which can't be implemented in the SPI bitbang framework, so there's needs for extension there. So the first thing that was factored out was support for standardizing the parameter checking and error handling that drivers need to do. So I said that you can vary many of the parameters per when you register the device, per message or per transfer. This means that drivers need to look in using the plain transfer function, need to look in 3 different places for configuration, and they need to do roughly the same thing for error checking a lot of the time. You know, it's a bit more complicated to implement the error handling code than it is to just say, I support these settings, please implement them. And there's some things that a lot of drivers just didn't bother doing, either because they assumed that users would never pass them bad data, or because they just weren't implementing a feature, so they didn't have any code for it at all, including error checking. So this has now been factored out to the core. It makes things more standard, it makes things more robust. It saves a bit of work for individual driver authors. I mean, it's not terribly exciting, but it was the first bit of work towards simplifying drivers. Actually, it wasn't the first bit of work towards simplifying drivers. Sorry, getting ahead of myself. The first bit of work towards simplifying drivers was that the message queue, where we take the messages in an atomic context, queue them up in a thread and send them to the hardware, was factored out. So this was done by Linus Valet a couple of years ago, almost exactly a couple of years ago. It was merged in May 2012. This implements some of what SPI bitbang did in the framework in a place that it's a bit more obvious that other drivers should use it. There is a bit of a difference with SPI bitbang in that it works at the message level. This is because there are optimizations that can be done at the message level that can't be done at the transfer level. And in fact, the driver Linus was working on when he did this, the PL22 driver, does a lot of these or some of these optimizations. So transfer one message, or doing things as transfer one message rather than doing it per transfer, means that we can use this standardized code, which literally every driver should be using. We can use this code even if the driver wants to do these fancy optimizations. Ideally, we'll factor them out into the core, but we're not there yet. So as well as transfer one message, this also implements prepare and unprepare transfer hardware operations. These are for powering on and off the SPI controller, so it's only powered up when in use, which, again, that's something that drivers needed to open code. They couldn't do it so easily in SPI bitbang. So it gives us improved power performance. And in fact, for almost all drivers, prepared transfer hardware and unprepared transfer hardware should just be runtime PM get sync and runtime PM put. So the drivers can actually set a flag when they register themselves, which will cause those functions to be called without them having to actually go and implement these functions. One other small but nice thing that the standard message queue code that Linus contributed did was it provided a way of setting the scheduler priority of the thread that pushes messages into the device. It's called the message pump. This is a technique that system integrators commonly use to manage the performance of the system, saying this SPI controller is really important, I want to run it as fast as possible, please schedule it with the highest possible priority, or this one's less important, give it less priority. It's very easy to do. You can easily hack the code in, but having it as standardized code that you can easily just tweak a setting for means that not only can system integrators discover this more easily, but they can implement it more. They don't need to go in and hack the code. They can just tune it at runtime, which makes everybody's life easier. So that wasn't as high level as SPI bitbang. So we've also subsequently gone and implemented the loop that splits things up into transfers within the framework 2. This offers no advantage at all over SPI bitbang, except that it's not called SPI bitbang. So we're now seeing a huge raft of drivers converted over to use this, which will just generally increase the overall quality and robustness of the system. As we've gone through and converted things, we've often found bugs. And in actual fact, the thing pushing some of the drivers to be converted is a bug fix patch. And the observation that they could just use the framework code and not have the bug that way too. This also will provide the basis for implementing some of the optimizations I keep mentioning. The loop will be extended to support them. Another bit of code that lots of drivers needed was support for DMA mapping. Before you can DMA to or from a device, you need to map the memory for access by the device. That's fairly straightforward. Essentially, every driver that was doing DMA was doing that bit. However, there were a couple of bits that not every driver was doing. One issue is that buffers may not be physically contiguous. So depending on how the buffer has been allocated and when it was allocated, it may, a contiguous set of virtual addresses that the kernel normally deals with may actually be laid out in non-contiguously in memory. So in order to cope with this, the driver should really map each page size of data individually. There were 2 drivers that did that. So a bunch of drivers that were doing, client drivers doing things like firmware downloads that transferred large amounts of data didn't work if they were running on the wrong SPI controller. There's also a slight gotcha in that addresses allocated using vmalloc need to be mapped differently because of very good reasons. And there was exactly 1 driver that coped with that. So factoring this out in the core will increase the correctness. It's not very widely adopted yet. Hopefully it will be a bit more widely adopted soon. But factoring this out of the core will increase the robustness of the stack, make sure everybody deals with all these cases, and it'll avoid everybody having to implement lots of fiddly little code to do this. The way the framework feature works is pretty simple. Drivers provide this can DMA callback, which is called for every transfer. If that callback is present and returns true, then when the driver gets called to do the transfer, it will have the buffers mapped as SG lists already. So it can just take the SG lists, hand them over to DMA engine, and with any parameters it needs, and job done. Finally, in terms of features that have been implemented in the framework recently, we have support for dual and quad modes. So I described them earlier. The implementation is in the framework is very simple because it's got almost no impact on software. It's basically only visible to hardware. Drivers can set flags on transfers to enable dual and quad mode. And when you register a device, the device registration code can flag up that this is possible. So if you've got a controller that can support dual mode and a device that can support quad mode, that doesn't mean that the hardware has actually been wired up to allow it. So that capability stuff allows the driver to work on systems where the hardware designer, for whatever reason, hasn't chosen to enable this. So yeah, and that code was contributed by Wang Yuhang. I think I had trouble parsing his name, and it was merged in 3.12. So what's next for SPI? Well, there's a couple of more things that we can do in terms of factoring out common code. And I've mentioned that there's optimizations that you can do per message. That's the main focus. So in terms of factoring things out, the big thing is handling GPIO-based chip selects. So sometimes SPI controllers have physical chip select signals that are integrated at the SPI controller and managed with varying degrees of autonomy by the SPI controller. Sometimes they don't. Sometimes they're only GPIO signals. And sometimes, even if the physical signals exist in the controller, the hardware designer will, for whatever reason, have chosen to use a GPIO, or maybe the physical signals in the controller don't actually work very well, and people just put the pin into GPIO mode using pin mux. This is not a very exciting feature, and the registration of the GPIOs is a bit fiddly to do at device registration time. But currently, the framework doesn't actually help with that at all. So every driver that wants to implement GPIO chip selects has to go and open code that, which both means that the feature isn't as widely available as it should be, and means that it's slightly more complicated to use than it should be, because you have to look at how your individual SPI controller driver has done things and cope with that. So if we factor this out into the core, so there's a standard way for people doing board registration to say, I have this chip select signal which is controlled by GPIO. That will make everybody's lives easier, it'll make the feature more widely distributed, and save everybody time. So in terms of features, that's about it. Non-performance features, I should say, that's about it. What's going on in terms of performance? Well, first, let's look at a simple example of what happens when you call SPI sync, which, like I say, is what almost all drivers do. We've got three execution contexts. We've got the device driver, which is requesting the transfer. We've got the SPI message pump thread, which is responsible for driving things into the hardware. And we have the hardware itself and the interrupt that it generates when it's done. So the device driver will call SPI sync, which will call SPI async. It will put the transfer, by the way, this example is for a simple single transfer message, just for simplicity, because the slide's only so big. So it'll queue the transfer up, it'll put it on the queue. Then it will kick the SPI thread, tell it to run, and it will wait for the SPI thread to run. Now, the SPI thread may run immediately on a lightly loaded system, but on a heavily loaded system, the CPUs may all be running flat out, doing something else. So so you get a delay here, potentially, while the scheduler waits to decide that the SPI thread should run. And this might take many milliseconds. It's not a quick case of microseconds, it's a noticeable delay. It's very, very obvious when you put a scope on the SPI bus. The SPI thread will then wake up, it'll look at the message, see it's got a transfer in it. It will start the transfer, which will start in the hardware immediately, and then it will wait for that to complete. Now, what currently happens is that when that happens, there will be an interrupt. That will wake the SPI thread up. The SPI thread, again, needs to wait for a chance to run. May happen immediately, may not. And all it's really going to do there, in the case of SPI sync, is wake the driver up, decide the message is finished, and it will wake the driver up again. You now need to wait for the driver to get a chance to run. The scheduler might have something else that's got more priority. And finally, the device driver will get back control. And if what it wants to do next is send another SPI message, then we go right back to here with all the delays. So we're spending a lot of time in this process on a heavily loaded system, waiting for the scheduler to run. You will, in really bad cases, frequently see that the time that the SPI bus is actually transferring data is much, much less than the amount of time that the SPI bus is sitting idle waiting for something to happen. And this can be a real problem if you're doing anything performance sensitive. So if, for example, you're reading an application off a SPI flash, you might be sitting there taking ages to start up while whatever else is burning your CPU time sits and burns your CPU time. So what we want to do is eliminate as many of these scheduling delays as we possibly can and keep the hardware as busy as we can. We don't want it sitting around doing nothing, being lazy. So I mentioned that SPI async can give you a bit of a performance boost. That performance boost is pretty trivial. All that it does is means you can queue multiple transfers up at once, or messages up at once. And so then what happens is that when the SPI thread gets woken up, it can immediately start the next transfer instead of having to wait for the device driver to get a chance to run again. That does get rid of one of the delays, but it also means that the SPI driver, the SPI client driver, needs to be explicitly coded to do this, and it needs to deal with the fact that it's going to get asynchronous callbacks. Sometimes that's worth it, and there's generally always a benefit to doing it if you can do it, but it's more work, it's harder to use, and at the minute nobody does it pretty much, so it's not a widely available benefit. And it's implementing optimization at in the wrong place as well. It's implementing it furthest out from the center of the stack, rather than in the center of the stack where everything can take advantage of it. So the simplest thing we can do, which is very easy to implement and will probably be implemented very, very soon, is to attack the same problem from the other end and do the wake up of the device driver in the hardware context. So instead of just waking up the SPI thread, we can see if the message is complete. If the message is complete, we can wake both the SPI thread, in case there's more work to do, and the device driver up. Again, that cuts out the scheduling delay in the same way that SPI async does, but it does it in a place where every driver automatically gets to take advantage of it. So it's going to have much more benefit. We still, however, have this delay here. And really, in most systems, that's not achieving a huge amount. So in most systems, SPI buses don't have more than one device on them. In most systems, each SPI bus has a single device on it. So there's never, and usually that device drivers tend to be fairly single-threaded. So there is rarely contention for the queue to interact with the hardware, and almost all drivers, I think there's 2 drivers in mainline plus 2 frameworks which use SPI async, so almost all drivers use SPI sync. So really this entire queuing mechanism here in the SPI thread is it's overhead. It's not doing anything useful. So ideally, we would be able to implement the overhead associated with the SPI thread and just immediately, when we queue the transfer, we immediately say, right, the SPI controller is idle. We don't need to worry about blocking here because we're running in SPI sync. There's no actual atomicity requirement. We can immediately go to starting the transfer, and then when we complete the transfer, we just need to go directly back to waking up the device driver. That will benefit essentially all users and will eliminate all the scheduling overhead that we can. So we're just down to the one scheduling overhead for getting back to the device driver. And if the device driver is used SPI async, then we should be able to start the next transfer directly in the hardware context as well for most users. So we're able to keep the hardware busy without waiting for the device driver to run at all. The problem with doing this is that the API does support the asynchronous users, and it does support some settings changes which can't be implemented in hardware context. So we have to have fallbacks that allow us to use the SPI thread. But, like I say, hopefully we will be able to implement code, or we will be able to implement code which recognizes when we're not in these special cases and allows us to implement this picture.
With two devices on one bus, automatically cause you to fall back to a schedule?
So would two devices on one bus automatically cause you to fall back to scheduling? I would expect not. I would expect that the implementation would actually be to look, is the device busy? If so, or is A, is the device busy, or B, am I in atomic context? If so, Q. Rather than just saying, no, don't do that. Because even if there's only one device on the bus, you still have to accept the possibility that something might decide to call SPI async. So you can't just say there's one device, we don't need a queue. And conversely, if you have two devices on the bus, they might not run at the same time anyway, so there's no... and you could also potentially queue things up. If there is queuing, you could potentially queue things up without scheduling the thread, because if you can block, you can put things on the queue immediately. So what else can we do for latency? One very, very small thing we can do, which does have an advantage on extremely heavily loaded systems, is we can do the DMA mapping and some of the other setup we may need to do for one transfer while the previous transfer runs. It's not a big win, but it is a win. And the other thing we can do that's fairly obvious, a bit fiddly to implement, hopefully we'll get to it soon, is we can coalesce multiple transfers in a message so that we use the hardware scatter-gather support that most DMA controllers have, if we're using DMA, and do the entire transfer, or do the entire message rather, without ever having to involve the controller. So if, for example, you've got a register write followed by a firmware download, it's quite a common access pattern, then you can send the command for the register write and the data is two separate messages usually, or you will send the command and data as two separate transfers usually. Sorry, I keep stepping over myself. And this will allow us to just do one transfer at the physical level. There's a guy called Martin Sparl, who I don't think is here, who has been doing a lot of work on optimizing an application he's got on the Raspberry Pi, which saturates a CAN bus. Now, the Raspberry Pi is not a very fast CPU, and a CAN bus is quite a high bandwidth bus. So his SPI-based CAN controller is very, very, very stressful for the system, and he's hitting essentially all the cases with you might see with the scheduler getting in the way. So he's really been drilling into trying to optimize these cases. And one of the things he's come up with is the idea of pre-validating messages. So in some applications, including his, there are some messages that get sent to the SPI device repeatedly. So for example, you might have a start working command and a stop working command. You want to send these relatively often. But all the error checking and all the mapping and so on that the SPI framework needs to do before it sends the command to the hardware, at the minute the SPI framework just sees every transmission as a completely new message. It has no idea that anything's been done before. So it'll go through, it'll loop through the entire message, it'll do mapping, it'll blah, 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 do a bunch of work. Martin has realized that this is actually a waste of time. You can just say to the SPI framework, here's a message. I'm going to send it a lot of times. Can you please check it and do any initialization you need to do? And then I'll give it back to you. I promise I won't change it. And this means on the resubmissions, you can go pretty much directly to sending it to the hardware. It's not a huge win for most users. I imagine most users will not bother using it, but Martin can measure a few percentage points improvement on his 100% loaded CPU, so it's definitely worthwhile. The next level of optimization that Martin's come up with is something that's not going to be generally applicable because he's exploiting some quite nice features of the Raspberry Pi SPI and DMA and GPIO controllers. But he's realized that he can implement the entire message queue, including manipulating chip select and things like that, in DMA transfers. So the DMA engine is as capable of writing to the controller control registers as it is of writing to the controller data FIFOs. So, especially in conjunction with the pre-validated messages, we can get some really nice performance improvements because we could just add something to the controller queue. The controller will do everything in hardware. It will generate interrupts at the right moment, and we're doing very little work in the CPU. The numbers are really quite nice. However, this does depend on the controller being able to do all the things we need it to do, and it does require some extensions to DMA engine. Currently, DMA engine doesn't really have the idea that you can build things up in quite the way that this work needs. But it will be very nice work if we can get it done. And it will be especially nice if we can get it done in a way that it's implemented in the framework and any SPI controller with the physical capability of implementing these optimizations is able to take advantage of it. So that's roughly where we're at, and that's roughly what our future plans are. SPI is a trivial bus. That's its major advantage for the hardware engineers. But because it can run quite fast, it's not so simple for software to work with. The overheads you have in things like scheduling start to matter quite easily with high bandwidth SPI applications. Until recently, the stack had been quite static, but recently there's been a lot more focus on improving things, both as a combination of new hardware and also of new applications. So the set of SPI devices that do things like have DSPs on them has increased. So we've had people focusing more and more on how quickly this thing runs and more on exploiting all the little corners of the SPI stack that mean that centralizing things is important so that we get consistent implementations and don't have to open code everything in individual drivers. So yeah, any additional questions?
Do you have any suggestions for SPI client drivers in terms of optimizing the code to make it work more efficiently?
Yeah, of course, yeah. So optimizations that client drivers can do, not really beyond what I mentioned with using SPI async. It's a pretty dumb, straightforward API, which maps fairly directly onto the protocol. So, I mean, obviously you can do silly things in your driver outside that aren't SPI specific, but in terms of SPI, the only thing you can really do to improve performance is use SPI async if you've got a stream of messages to send. So, for example, a sequence of register writes.
You mentioned a lot about SPI where the CPU is the master.
Yeah.
Hardware support being slave. Is any work being done on slave support for Linux?
Is anybody working on allowing Linux slave to be a SPI slave as opposed to SPI master? Not in mainline. I have seen things floating about in vendor trees. They were in vendor trees, so no, not in mainline.
Some of the things you mentioned, to what extent are they applicable for other stuff in SPI?
So all the techniques to do with scheduling are very generally applicable. I mean, you could do similar optimizations for I2C. There's not much point because I2C is so slow that the percentage of time that's spent waiting for the actual physical hardware it typically dominates any of the effects that we're trying to optimize here. But yeah, these techniques are pretty generally applicable. Any bus that's fairly high bandwidth will be able to and has similar hardware that needs lots of software management, doesn't just implement everything in the hardware, will need similar techniques, or be able to take advantage of similar techniques, I should say.
So the SPI bus doesn't implement any protocols, but there are families of peripheral chips that have common register interfaces.
Yeah.
Is there any directed effort to create sort of protocol layers on top of the SPI driver framework to support these families of chips?
So families of chips that support similar protocol layers. I mean, there is the RegMap framework, which is doing that at a very basic, just register read and write level. Otherwise, there's no directed effort that I'm aware of. But obviously, I would expect that most subsystem maintainers, if they saw a bunch of drivers coming in that had very similar code, they would be pushing back on the driver authors and saying, hey, you should join these things up. And some subsystems are essentially that sort of refactoring. I mean, something like ASOC, for example, the power management code within ASOC is an effort to factor out shared control things that are implemented in or that need to be implemented in roughly the same way for almost all codec devices. So, sort of.
I just wanted to say an example would be the MMC works quite well with a generic SPI.
Yes, that's true. Yes, MMC is one example, and actually Flash as well. So their Flash SPI Flash chips do have some per device configuration, but it's mostly just a big data table in a driver that does generic handling. So yeah, I mean there are examples, but they're not. I wouldn't say there's an organized effort to do it.
It's kind of related to what he was asking about, but I didn't see any controls for lock polarity, chip select polarity.
Yeah.
Is that buried in there? You just didn't talk?
Yeah. So I glossed over how clock polarity and chip select polarity are controlled right at the very start. There are flags you can set when you register the device for these things, and you can override them at least per message. Doing it per transfer would be that would be really exciting hardware. But yeah, you can control these things. I mentioned that there's things like SPI 3-wire mode, for example. So you just set a flag when you register the device, and the controller driver needs to implement it, but it's essentially invisible to software.
I'm the MTD maintainer. At the beginning, you mentioned you didn't want to talk about SPI Flash as much because that's my job, I guess. Are you aware of though any kind of hardware that actually is partially a pure SPI controller, but at the same time has pieces which accelerate Flash specifically, which would kind of then put it halfway?
Yeah. So am I aware of any Flash optimized SPI controllers that are actually really usable as generic SPI controllers? No. I keep worrying about that every time I see one of those optimized controller drivers get sent to me by mistake. But every one I've seen, it's been real contortions to make it usable for regular SPI. and I suspect that we will have to worry about it at some point because hardware engineers are creative and innovative people. But
Example for you, so maybe we can talk about it.
Oh dear. Yeah, let's talk. What?
I'm just wondering about small FIFOs. Is there, because typically a lot of messages are pretty small. Is there small FIFO in the driver so that whether it's in software or in hardware it can be taken advantage of?
There's nothing pure software, but yeah, if the hardware supports a FIFO, it will be exploited. I can't think what you would do with it in pure software because you will typically need to flip the chip select to at the end of a message. So yeah, you can flip the chip select at the end of every transfer if you want to optionally, but that's essentially just the same as sending 2 messages. So it's not really. It's there in the API. I'm not really sure why. That predates me. There was a question at the back as well.
I have a question. I have a driver that's not in mainline, which has several kernel threads, 4 in fact, that can talk to a chip via SPI, and they have real-time scheduling priorities that I've worked out the way things work now. So I had some questions about, with this optimization of a driver thread not scheduling and instead setting up the hardware directly and setting up the transaction. So will instead scheduling the SPI 1 thread have any effect if there's not a lot of concurrent transactions? Or?
So
I'd be able to talk to you afterwards more specific.
Yeah. So how does doing the transfer initiation in the driver context play if your driver context is a heavily optimized real-time driver context? I suspect that for applications like that, either you will want to schedule as quickly as you can, in which case it's not going to be a big deal, or you want to get it out of the driver context as quickly as you can because you want to let the driver context get on and do whatever it's doing at real-time priority. In the latter case, we would need to have an option where you could say, no, I really want to do this asynchronously, and maybe just calling SPI async would in fact be enough for that, or maybe we would need some other flag you could set to say don't do that, but yes, that is a valid concern, and we would probably need a way to say, yes, you think you can get away with it, but no, you can't. And I'm getting told I need to shut up now, so thank you all for your attention. Enjoy the rest of the conference.